Hello folks, this is Bryce Gernon here, and I'm here to give a quick review on partial derivatives and Laplace's equation. Partial derivatives of multivariable functions, of course. So, for this one, we're going to be going over exercise number 38 from section 13.3 of our textbook. And the problem is as follows. Given a function, which is f of x comma y, equals the natural log of x squared plus y squared. We have to show that it fulfills the conditions of Laplace's equation, which is that d squared z over dx squared plus d squared z over dy squared equals 0, which is just another way of saying f sub x plus f sub y equals 0. And this is going to be the notation that I'm going to be using because I prefer it, but you can use either one for this. All right, so we're going to start by taking the first partial derivatives of the function, starting with the one with respect to x, so f sub x of x comma y. And we're going to look at the inside of the function, and remember that we are holding y constant for this. It's going to count as a constant, so when we take the natural derivative of a log, we look at the inside of the function, and x squared is our only variable here, so we're just dealing with that as a variable, meaning we get 2x, and the y squared just disappears like any other constant would. And then, of course, for natural log, we have whatever is inside on the bottom for the derivative. Then we're going to do the partial derivative with respect to y of x comma y, and this is going to be very similar as you might expect, x squared plus y squared. This time we're just dealing with the y, so it equals 2y over x squared plus y squared. That's all well and good. Now time to move to the second order partial derivatives. So let's start with f sub x of x comma y. So for this, we are going to want to use the quotient rule of taking derivatives. For convenience's sake, I'm going to refer to the top part here as f of x, and the bottom part here is g of x, just because that is what is traditionally used in the quotient rule. So we are taking the quotient rule derivative here, keeping in mind that y is just a constant. And so that is going to be equal to g of x, which is x squared plus y squared, times f prime of x, which is just 2, minus f of x, which is 2x, times g prime of x. And keeping in mind, again, y squared is a constant. I know I keep saying that, but you got to remember that. So that's just going to be a 2x because we're just taking the derivative of x squared. Over g of x, g prime of, no, just g of x, sorry. Just g of x squared. There we go. So now we can simplify this a little bit. This is going to be equal to 2x squared plus 2y squared minus 4x squared over x squared plus y squared squared, which is just going to simplify down to negative 2x squared plus 2y squared over x squared plus y squared squared. Now we're going to take the second order partial derivatives with respect to y both times, and keeping in mind that when we do y, that means we take the partial derivative that starts with the y. So we take the first order partial derivative with respect to y, and then we differentiate that again with respect to y. So again, quotient rule, top is f of x, bottom is g of x, standard stuff. We're going to set this equal to, and then we're going to have g of x, x squared plus y squared, times f prime of x, 2, minus f of x, which is just 2y this time, times g prime of x. And again, we're taking this with respect to y this time. So even though g prime of x in the last was 2x, in this one it's going to be 2y, because in this case x is a constant, y is our variable. So we just get 2y again over x x squared plus y squared squared. You can already see these are starting to look pretty similar. That's a pretty good sign. So we're going to simplify this a little bit. We're going to get 2x squared plus 2y squared minus 4y squared over x squared plus y squared squared, which is going to simplify to 2x squared minus 2y squared over x squared plus y squared squared. And then we just plug these into Laplace's equation. Again, as a reminder, that is the second ordered partial derivative with respect to x both times, f sub x plus f sub y equals 0. So that is going to be negative, looking up here at our answers here and here, we're going to have negative 2x squared, just trying to keep everything in camera, plus 2y squared over x squared plus y squared squared plus 2x squared minus 2y squared over x squared plus y squared squared equals 0. And as we can see, negative 2x squared counters the 2x squared, 2y squared cancels the negative 2y squared, and we are left with 0, meaning this does satisfy Laplace's function, known as a harmonic equation. Lots of really cool stuff. All right, so if you want any more review on partial derivatives, I would highly recommend checking out pretty much all of WebWork Homework number 8. That has a lot of good stuff on partial derivatives, but especially problem number 11 I found really helpful. It has a lot of second-order derivatives, which are pretty much always going to be the most tricky when you're dealing with complex functions, like natural log, sine, cosine, stuff like that. So, yeah, that's pretty much it. I hope that you found this review helpful, and good luck on the exam, folks. Bye.